Okay. Huh? Where is that? This side also there. Okay.
So folks, how was the exam? Yeah? Was it tough or was it not so tough? How was the exam? Could you solve all the problems? Yeah? They're not very difficult. Were they? Which one was the most difficult? Are you sure you have understood everything that we did so far? By and large? Because now things are going to become a little bit more difficult. Okay? Because as you notice, we have brought in now asymmetric information into the picture. So far, we dealt with asymmetric information in a different format. We said we have a principal agent kind of a problem where we set up an optimization problem for the principal and imposed two constraints on the agent. One was the participation constraint, right? Which meant that the optimal contract had to give the agent at least his reservation utility. And the other constraint was the incentive compatibility constraint, where in the case where there are two work effort levels only, high and low, the incentive compatibility contract ensures that the agent actually works hard after taking the contract, right? Okay, so this is the way we dealt with it. Now, from today, we are going to bring in we are going to look at it in a game theoretic manner. So we are going to learn how to expand the general framework of Nash equilibrium in games. So far we will at the moment we will only concentrate on static games, right? So games which don't involve sequential moves, right? Okay, how to actually generalize the idea of a Nash equilibrium to a game with asymmetric or imperfect information, right? With imperfect information. The idea of the Nash equilibrium in this context will be what is called Bayesian Nash equilibrium. So we'll be looking at a Bayesian Nash equilibrium, B-A-Y-E-S-I-A-N, Bayesian Nash equilibrium, right? So that's what we'll try to define in today's class. That's the idea we'll try to understand, the idea of a Bayesian Nash equilibrium, right? Okay, so in this class, we will end by defining a Bayesian Nash equilibrium. I'll give you a quick overview of what the class will be. Right? Essentially, we will think of a situation where, think of two parties to a transaction. Okay, think of two parties to a transaction. This party 1 and party 2. Player 1 and player 2. Suppose player 2 can be of two different types. The player 1 is of a fixed type. Okay? The example would be in the Cournot model. Player 1 is firm 1, which has a fixed marginal cost of production. Firm 2 can actually have either a high marginal cost of production or a low marginal cost of production. We'll assume just to take an example, suppose firm 2 knows what its cost of production is, but firm 1 does not know what the cost of production for firm 2 is. all that firm 1 knows is firm 2 can be a low cost firm with a certain probability and a high cost firm with a certain probability. On the other hand, the low cost firm knows its own, the second firm knows its own cost of production, that it knows whether it's a low cost firm or a high cost firm, and also knows the cost of production of the first firm. Right? So there is an asymmetry of information here. You see the asymmetry of information here? Firm 1 knows that firm 2 can be a low cost or a high cost firm with certain probability. It doesn't know specifically whether firm 2 is a low cost or a high cost firm. Firm 1 obviously knows its own cost of production, but doesn't know of this about firm, only knows the probabilities with which firm 2 can be of various types. Firm 2 on the other hand knows specifically its own cost of production and of that marginal cost of production, and also the cost of production for firm 1. Right? This is a case of asymmetric information. Okay. In game theory context, you call it a case of imperfect information. Why would you call it a case of imperfect information? Because what you then say is that firm 2 is of 2 types: a high cost firm or a low cost firm. Firm 1 does not know what is the exact type of firm 2. It only knows that firm 2 can be a high cost firm with a certain probability, and firm 2 knows and firm 2 can be a low cost firm with a certain probability. Firm 2 knows its type and the type of firm 1. Right? Okay? So therefore it's a case of asymmetric information. Okay, so the general idea is, now obviously you understand that the output that firm 2 would produce will depend upon its own type. Output that firm 1 produces depends upon what firm 2 produces. So it's important for firm 2 to have certain beliefs about what the type of firm 2 is. Okay? So that's the next ingredient that we're going to bring into the picture. How does one understand, how does one analyze models where agents are required to form beliefs about the types of the other agents? Right? Because what other agents do depends upon what their types are, and obviously for the first agent it's important to know what the other agents are going to do, because ultimately it's a game, right? What you do depends upon what others would do, and therefore you need to form beliefs about the type of other agents, right? We will try to solve the Nash equilibria of such games. Okay, the Nash equilibrium of such a game is called a Bayesian Nash equilibrium. Why is a Bayesian Nash equilibrium? Because we are going to assume that player 1, for example, will form beliefs about the various types of players that player 2 can be using a rule called Bayes' rule of forming conditional probabilities. Right? Has anybody heard of Bayes' rule? A Bayes' theorem? No? So basically, think of the conditional probability that an event AI occurs given that the event B has occurred. Okay? The formula for this is right? This is the formula for the conditional problem. Everybody is familiar with this formula? P of A given B is the joint probability of A and B occurring divided by the marginal probability of the probability of B occurring. P of B. Right? Sure? If you are familiar with this formula, please look it up on Google and try and understand that well. Now, what is P of B? P of B is the probability that B occurs. Okay? find probability that B occurs, right? Okay, so POB is the probability. So this is Bayesian. Okay, fine. And we are going to say that players are going to form beliefs about their types, okay, the types of other players. So probability that the other player is of a type I, given that I know my own type, using this, right? Okay, and therefore when we solve for the Nash equilibrium of these such games, given that beliefs are formed using Bayesian rule, we actually call the equilibrium a Bayesian-Nash equilibrium. Bayesian-Nash equilibrium. Is this clear? Right? Sure? Everybody understands this well? This can further be internalized. So there are n possible outcomes, right? If there are n possible outcomes, sure. So then what is the probability of B? Probability is that B occurs given the A1 occurs. What is the probability B occurs given A2 occurs? Probability B occurs given A3 occurs. Given that A1, A2, A3 are all mutually exclusive outcomes, you can actually write it like this, right? Okay. So with this background, I will start by illustrating some simple. So let's basically start to and try to develop a simple model for as a beginning of the building blocks in this, right? So what is the additional thing that's going to come in when you think of Bayesian-Nash equilibria? Really, beliefs. So now we are thinking of agents as being agents of different types, and players having to form beliefs about what type of particular agent is, and the idea is then to solve for Nash equilibria of such games. Right? So I first solve for Nash equilibrium like this for a very simple game, and then we put together all the building blocks and definitions, so on. So by the end of the class, we'll have a working definition of a Bayesian-Nash equilibrium, right? And then we'll take some examples so that we will learn how to actually solve games at that time. Right? Or if you can solve such simple normal Nash equilibria games, right? You can find mixed strategy solution, equilibria, pure strategy, and right? So this is the additional bit that we have to do. Okay. So now, first, just to contrast this with a simple Cournot game, right? I'm going to use a Cournot model, right? Because that's all of us are familiar. Okay? In the Cournot model, there are two forms and all that, right? So first we will put some forms, and then I'm going to assume I'm going to bring in a Bayesian-Nash kind of a thing. So I'm going to have two different solutions, and I'm going to compare the two different solutions. Okay? So let's start with a simple example. For example, as an application of this, an auction is a classic example of a game with imperfect information. Because when you are bidding for something, you know your own valuations, but you do not know the valuations of all the other people who are bidding for the, right? When these are sealed bid auctions, where, for example, you want to undertake a project for the university, and all of your contractors, and you have to put in sealed bids, right? Of how much you will spend, how much you will be willing to do this job for, right? Okay, then what you're really doing is a sealed bid auction, right? And the lowest bidder will win the auction. Right? Person who bids the lowest for building a building in the university will bid, right? Okay, so obviously, how much others have bid matters for you. You know your own bid, right? We do not know what is the bid for others. So we'll actually also study auctions quite a lot in this framework, right? Different types of auctions, different auctioning rules, and so on, right? The other thing, it will become even more interesting when we look at dynamic, because when dynamic games are very interesting kind of a possibility open. What is the possibility? That suppose it is important for me to make you believe that I am an agent of, I'm of a particular type. Yeah, for example, suppose I'm a monopolist in a firm, right? Okay, in an in an industry, and you are wanting to come into the industry. I want to tell you that if you enter the industry, I will fight you. I'll set price equal to margin cost. It will not pay. Right? You know, for example, in a one-shot game that it doesn't pay for me to actually, because that's not the sub-game perfect Nash equilibrium. But if I have a dynamic game where I'm going to choose first, then I'm going to choose, then I'm going to choose again, I might actually want to develop reputation for being tough. So I might actually want to mislead you into believing, I want to actually take action which will make you believe that I'm of a certain type. So I might actually manipulate your actions. Right? This is called signaling. Right? This is called signaling. So signaling strategies will become important when you think of dynamically. The agent might pretend to, might want to strategically manipulate the beliefs of other people about their own types. On the other hand, the person who is entering the person who wants to enter the industry might actually want to find what my real type is, which is called screening. So look at signaling and screening equilibrium will be the real important part when you think of, because those will be very important for our next module, which is on the industrial organization. Right? How do firms set prices? How do firms behave in a strategic environment? Right? That's really the important part that we're going to look at. So fine. So let me think of a simple model. First, surprise. A minus Q, okay? Or let's assume, for simplicity, that both these firms have a. Okay, so let's think of it. C1, C of Q1, C1 Q1, C of Q2, C2. That's a simple Cournot game with perfect information. So basically price is A minus Q. Q is total quantity, Q1 plus Q2, right? The cost function of the first firm is C1 Q1. The cost of the second firm is C2 Q2. Right? So first, let's solve this. Right? Okay. What is it that the first firm wants? For the first firm, then, profit of the first firm is profit of the first term is this, A Q1 minus Q1 Q2 minus Q1 square minus C1 Q1. Everybody gets this? Okay. So how do you maximize this? Yeah? Or Q1 is equal to A minus Q2 minus C1 upon 2. Right? What will be Q2? What will be Q2? So think of pi 2. Right? Differentiate this. That's true. Right? Now, can you solve for Q1 and Q2? How will you solve for Q1 and Q2? So, simply substitute, right? So, if you solve, what you get? So, you get A minus, substitute for Q2, yeah? Sure?
A minus Q2 minus C1.
This is Q1. So what am I doing is, so in this equation, I am just writing Q1 is equal to A minus Q1 equal to 1, 2. Right? Sure? So this is what? This is equal to Q1 minus A by 2. Yeah? Which is equal to? Z12 plus. Yeah? So if you solve this, what do you get? If you solve this, what do you get for Q1?
Q1 is equal to A plus C2.
So we get Q1 is
A plus C2 minus 2C1. The whole thing divided by 3.
by
The whole thing total divided by 3.
okay. And what do you get for Q2? Yeah? Right? So you see the logical outcome. So higher the C2, higher is Q1. Higher the C1, lower is Q1. You can understand why, of course, higher the C1, lower will be Q1, because higher the marginal cost, right? Low of output, lower will be Q1. But what do you think about C2? Why is Q1 higher if C2 is higher?
Because demand for Q2 will reduce. Demand for Q2 will reduce.
Because Q2 will reduce its output. Because higher cost for for the second firm would mean that the second firm produces less and therefore the first firm produces more. Right? First firm produces more. Right? That's the standard Cournot game. Sure? So the cost of production of the first firm goes up, the second firm, because of the second firm produces more. The optimal response second firm is to produce more. Right? Now I want to make this a little, I want to complicate this a little bit. Right? I'm going to say, So clearly, knowing what the cost of production of the second firm is important to the first firm. Knowing what the cost of production of the second firm is important for the first firm, right? Okay? Is this clear to everybody? Everybody understands this? Okay. Now I'm going to make it a little bit more complicated. I'm going to say that the first firm has a fixed marginal cost, but the second firm can be either a high cost firm or a low cost firm, and the first firm does not know for sure whether it's a high cost firm or a low cost firm. All that the first firm knows is that the second firm is a high cost firm with a certain probability and a low cost firm with a certain probability. Right? Sure? And therefore the first firm has to form expectations, has to form beliefs about what the second firm is. Right? That's the kind of a structure that I'm going to bring in. Okay? First, as a very simple kind of a model, and then we're going to complicate it by using symbols and by